Welcome students. In this lecture, we will discuss the first law of thermodynamics. Before going to discuss the first law of thermodynamics, we need to understand the relationship between heat, work and the concept of internal energy. Just like mass, energy is neither created nor destroyed, but it can be changed into different forms. Internal energy is a thermodynamic property of the system that refers to the energy associated with the molecules of the system. And when a system goes through any change due to interactions of heat, work and internal energy, it is followed by various energy transfer and the conversions. But during this transfer, there is no net change in the total energy. For example, water can be decomposed by electric current into gaseous hydrogen and oxygen, and it is found that 285.8 kilojoule of electrical energy is used to decompose 1 mole of water, and this energy must have been stored in hydrogen and oxygen, since the same amount of energy in the form of heat is released when 1 mole of water is obtained from gaseous hydrogen and oxygen. Thus, the 285.8 kilojoule of electrical energy which was supplied to the system has been recovered later as heat energy. And second example is, in the operation of an electric fan, the electrical energy which is consumed is converted into mechanical work which moves the blade. According to first law of thermodynamics, energy can neither be created nor destroyed. That means the energy of the universe is constant. And the first law of thermodynamics states that the heat is a form of energy and the energy of the universe remains same, though it may be exchanged between system and the surroundings. It cannot be created nor destroyed. And the energy of the system that is isolated from its surrounding is constant. The internal energy of a system can be increased in two ways. First, by supplying heat to the system, and second by doing work on the system. Suppose the initial internal energy of the system is U1. If it absorbs heat Q, its internal energy will become Q1 plus U1 plus Q. If further work W is done on the system, the internal energy will further increase and become U1 plus Q plus W. Let us call this final internal energy as U2. Then U2 is equal to U1 plus Q plus W, or U2 minus U1 is equal to Q plus W, and delta U is equal to Q plus W, and this equation is the mathematical form of the first law of thermodynamics. And if the work done is the work of expansion, then W is equal to minus P delta V, where delta V is the change in volume and P is the external pressure. Then the equation would be delta U is equal to Q minus P delta V, or Q is equal to delta U plus P delta V. Now, two interesting results follow from the mathematical formulation of the first law of thermodynamics. Neither Q nor W is a state function, but at the quantity Q plus W, then that is equal to delta U is a state function, because delta U is a state function. During isothermal process, delta U is equal to 0 and Q is equal to minus W, because internal energy of an ideal gas is a function of temperature. Hence, for an ideal gas undergoing an isothermal change, delta U is equal to 0. In this case, that means the heat absorbed by the system is equal to work done by the system. And during isochoric process, delta V is equal to 0 and W is equal to P dV and delta U is equal to QV. That means change in internal energy is equal to heat exchange with the surroundings at constant volume. And for adiabatic process, Q is equal to 0, delta U is equal to W. That means internal energy change is equal to work done on the system. And first law of thermodynamics provides information about energy changes in chemical reactions. That's for all today. Thank you.